Okay, good afternoon, ladies and gentlemen. We're going to, this is the practical side of it, lab number 5, I think. This is a special lab I made for you. I was planning to do to do this in two labs. Lab 1, just a simple experiment of NMR, then lab number 2, interpretation of proton NMR of aspirin and paracetamol, but because we don't have time and we don't know what's going to happen, we do it both together. Okay, so we kind of need to be sort of quick. So what we're going to do, we're going to see a simple NMR instrument and simple NMR experiment, how we perform that, and then we're going to interpret the proton NMR spectrum for aspirin and paracetamol. Okay, so these things are important to remember. What is the structure of aspirin and structure of paracetamol, how NMR can help us determine these structures. Okay, this is what we're going to answer today. Right, so intended learning outcomes, we're going to perform basic NMR experiment, very easy, very straightforward. And then we're going to interpret the proton NMR spectra. This is a plural for spectrum for aspirin and paracetamol. Okay, very quick recap. In NMR, whether it is proton NMR or carbon-13 NMR, we have several things that we need to look for. Okay, so we're going to focus on proton NMR, right? So we're not doing any today is nothing to do with carbon-13 NMR. Therefore, we have four important points. One, number of signals. So 1, 2, 3, 4, 5. That tells me there is 5 different hydrogen environment. It means there is 5 hydrogens in the molecule that they have different environment. They are chemically non-equivalent. Okay, chemical shift. What does chemical shift tell us? Well, it's low field or high field, but usually we call it upfield and downfield. If it is upfield around this area, that means that proton is not near it's not near the electronegative atom. No, it's not near a benzene ring. It's usually alkyls such as methyl, ethyl, propyl, those kind of things that they're just neutral kind of molecules. So the if it is down here, it will tell us about it tell us that this proton is somehow near oxygen, nitrogen, fluorine, chlorine, bromine, iodine, or benzene rings. Okay, and it's de-shielded for that reason. So basically, chemical shift reveals what is a chemical environment of the proton. Multiplicity or splitting patterns that will tell us about the neighbors. So this is two signal, one signal, two signal. This signal is a singlet. It means there is no neighbor next to it, right? There's no neighbor next to it. And this one is a triplet. That means there's two neighbors, two hydrogen neighbors next to it. So it shows the number of protons residing on directly adjacent atoms, adjacent carbon. Obviously, atoms is carbons in this case. Adjacent is neighbor, next to. Okay, so that's how we find out number of signals, where the signals is residing, and what are the neighbors. One hydrogen, two hydrogen, three hydrogen. So eventually the area under the peak, okay, area under the peak, which is called integration, will tell us how many hydrogens making up that peak. So if you have a signal here, okay, that might be for one hydrogen, that might be for two hydrogen, that might be for three hydrogens. Okay, so these four things are very important. Remember them. Now, another important thing is this is TMS that we've been talking about. TMS is basically silicon with 4 methyl group attached to it. Why are we using this and why we uh, assuming that ppm for TMS is 0? Why? Because look, this is the maximum. This is the maximum hydrogen involved. There's 3, 4 times, that's 12 hydrogens. And these 12 hydrogens, they are all equal, one environment. So we get longest longest signal, which is for 12 hydrogen, and not 12 hydrogen, okay, give us the longest signal. And because they are all fully shielded, why? Because there is no benzene ring, there is no oxygen, nitrogen, there is no silicon, there is no fluoride, chloride, bromide, iodide next to it. So these hydrogens are fully shielded. Fully shielded means they are really upfield, the most upfield hydrogens you can find. Therefore, we call it 0 ppm. It's not 0, but we just call it 0 as a reference. Okay, we start from there. So usually when we do NMR, proton NMR, we add TMS into our sample, okay, as an internal standards. So we get TMS signal, and that's it's like a lighthouse. It will guide us into the rest of them. Okay. Now, the solvents that we're using, ladies and gentlemen, for solvents that we're using for NMR, proton NMR specifically, should not have hydrogens in it. So we can't use water. Why is that? Think of it. Think of it. If you're using water, okay, or chloroform, DHCl3, or DHSO, well, these hydrogens will participate or take part in NMR spectrum, and that's not what we want, because that is not a real NMR spectrum. It's a fake one. So what do we use? We use different isotope of hydrogen. Hydrogen 1 is one isotope. Deuterium 2 is another isotope of hydrogen. Deuterium 3, it is another. So hydrogen has 3 isotopes. Isotope 1, 2, and 3. This is called proton. This is called deuterium. This is called tritium. And we call that deuterated chloroform, right? Deuterated chloroform. So there is no hydrogens of them. And this deuterium is actually NMR inactive. Why? Because the number of protons and the number of neutrons equals to an even number. And you remember we said an even number, it doesn't work, right? Well, you might say deuterium, it should work, maybe, but at the moment we're not using deuterium, we're using deuterium, and that's the reason we're using deuterium. Okay, so what's a deuterium? It's an isotope of hydrogen. So instead of H2O, we use D2O. D2O is heavy water. We call it heavy water. What's a heavy water? It's a water which is a little bit heavier than usual water. Is it drinkable? No, I don't think so. So don't drink it. You can't even find it. Okay, so it's not like usual water. You can find it everywhere. Okay, now what we do, we go into the simulation straight away, right? And then we go to the simulations, and then we're going to do that. Right, let's keep this. Yes, keep this for us, and then we're going to. Okay, I'm gonna copy. I don't know why it didn't let me, but I'm gonna copy anyway. So. Right, so if you click it, you go straight into the virtual lab, ladies and gentlemen. The virtual lab is nuclear magnetic resonance spectroscopy and evaluation of simple proton NMR spectra of selected organic compounds. Okay, prepare your report as well. Okay, but you know, whatever we're doing, we're not doing any I don't know, maybe you're not doing any method and things like that. So just prepare a lab report, a lab diary. So when you go back to when we go back to the actual lab, we will inspect it. Okay, so the aim is this. As we've been doing it before, we know what to do. The theory here, I'll give you a lot of things to read about NMR. So I encourage you to read it. The pretest as well will help you if you have a chance. Do a pretest, see if you understand NMR, and then do a post test after you do the experiment. This will help you because it gives you the correct answers as well. Procedures here is simple. It's very simple. Do not right click and things like that. Write in the procedure whatever we're doing. Okay, whatever exactly we're doing. And you remember this thing, yes? In the box, it says click on the benzene option in the apparatus menu to introduce it into the workplace. So we're adding benzene. That's benzene. So we're doing proton NMR for benzene. See what we get. Benzene. No derivative, just benzene. Let's take a NMR tube. This tube actually is called NMR tube. What we do, we put a sample in it and put it in a spectrometer. Not spectrophotometer, spectrometer. So this is an NMR spectrometer. Okay, this is the magnet, the full magnet, which gives us the external magnetic field. Now what we do, right, we're going to read this. Click on beaker. I'm clicking on it. So I get about 5 milliliter or 10 milliliter. I'll add it into the tube. Okay, so I've got it in the tube. So I'll click the tube. Okay, I put it in the probe. Now it goes completely different place. So what happens, you pick up that and you put it inside, in the heart of the magnetic fields. We call that probe. Okay, so what we do, click on the observe button to observe what's happening inside the NMR spirit. So now basically that's all it is. You have benzene, which is liquid. You put it in the tube, NMR tube, and you put it inside the NMR, the probe of the NMR, which is in the heart of the magnetic field. Just like we human beings, we go inside the scanner when you do MRI. Okay, what we do, we go inside the tanuraka. Okay, we call it tanuriya, right? Why we call it ash'a? Because it looks like a tanur, right? Maybe. So we're going inside that tanur, okay, and the sample goes inside that tanur, okay. Yeah, so it goes inside it where the magnetic fields can have a great effect on the sample. Now what we do, we observe. Look what's happening. Look what's happening. There's the sample here. So the magnetic field south and north, okay, has a great effect on these protons here. These protons will align themselves either parallel or unparalleled to the magnetic fields. Then what we do, we send radio frequency in. The little magnets of proton magnets, they're spinning around. When the radio frequency hits, okay, we have a source of radio frequency here. As you can see, when the radio frequency hits the nucleus, it flips. Okay, it flips from alpha energy state to beta energy state. Then when it returns to alpha energy state, it will emit the same amount of radio frequency energy, and then we will receive that radio frequency energy here by a receiver. Then we'll send it on to a detector and we'll find out what's happening. That detector will give us, using a computer, we will get a proper NMR, proton NMR spectrum with different signals for the sample. Okay. Now, that's all of it. What you can do, you can restart again, right? And then basically just do that. This is the whole experiment. It's straightforward and easy. Now we're going to observe again. See, the radio frequency is coming in. Look, and it's spinning. The nucleus is spinning. And we're actually doing proton NMR for benzene. Then what do we get? What do we get? We observe. Okay, you click observe again and you get the spectrum. Please re-draw this spectrum in your lab books. Okay, so start from 0. It can go from that side or from that side. It doesn't matter really, as long as you put here TMS, and you see we only get one signal at around 7.6. Why one signal? Because benzene ring, we talked about it, is a symmetrical. All the protons are in the same environment. They all get exactly the same signal. And this signal is for 6 proton, because a benzene ring contains 6 protons, right? This is it. And that is all what we did. So draw this and talk about it as well and say, this is, this is a chemical shift. This is TMS. This is benzene. We get one signal because we have 6 hydrogen, but they are all chemically equivalent, and all the signals will be on the same area. Therefore, what we have a long signal which is integrated for 6 hydrogens, 6 protons, aromatic protons. Okay, that was it. And let's go to the other thing. Let's go to proton NMR spectrum of aspirin. and paracetamol. Okay, this is important here. So this is not benzene anymore. This is a benzene ring, yes, as you can see, this is a benzene ring, but this is not simple benzene ring. This is a derivative. Aspirin, okay, is basically salicylic acid acetate. So that is the acetate for it. Okay, this part is the acetate, and this is salicylic acid. The rest of it is salicylic acid, and that's what it is. It's salicylic acid acetate. Okay, good. We're going to see what happens to the in the case of proton NMR for aspirin. This is what we get. This is a TMS. Okay, that's it. We get TMS. This is nothing, probably just impurities. We get 1, okay, and 2 and 3 and 4 signals. Why we get 4 signals? In fact, looks like 4 signals, but here, this area, okay, is overlapped and is 1, 2, 3 signals. So you have 1, 2, 3, 4, 5, 6 signals, indicating 6 hydrogen environment. How do we know that? This is not easy to see. You see, this is it. It's overlapped and it's not easy to interpret. What I do, I will help you with that. Before that, I need to erase all these. Where's the eraser? Okay, so I'm going to remove all this. Right. Sorry, not laser, eraser. It's all, okay, that's good. Very handy. So I'll use the pen instead of the laser. Now, this is the structure of aspirin. Okay, I'm not going to draw unnecessary, but we're going to number everything on the structure. So not just carbons. We start from here, 1, and that's another carbon, 2, oxygen 3, okay, another oxygen 4, that carbon here 5, there's a carbon there 6, carbon 7, carbon 8, carbon 9, carbon 10. Then we go to another carbon which is 11, then that oxygen is 12, okay, and that oxygen is 13, right? We haven't counted any hydrogen. There is a hydrogen here, yes, and I'm just going to do line so we know there's a hydrogen there. There's another hydrogen there. Do we have hydrogen here? No. Hydrogen here? No. So that's all the hydrogens we have. In fact, I'm going to draw more. Do we have any hydrogen here on this carbon 5? No. There's 1 bond, 2 bond, 3, 4 bonds. So no hydrogen for this carbon. And this carbon here, 1, 2, 3, 4, no hydrogen for that one. So how many hydrogens I have? This is 1 hydrogen, 1 environment, CH3. Yes, they are 3 hydrogen, but they equivalent. Good. There is 1 other hydrogen here, okay, that next connected to the oxygen, and I have another one here, okay, which we call a 6. There's another one we call a 7. There's another one we call it 8, and there is another hydrogen we call it 9. We call this one 1, and we call that hydrogen 13. Now, simple as that. The 13, there is no neighbor at all, okay, and it's connected to oxygen, so it's de-shielded, and there is a carbonyl group here as well, so this is fully de-shielded and therefore goes all the way down to 12. So just one signal here, a singlet for hydrogen 13, no splitting. Why? There's no neighbor. Okay, then we go to the other easier one, number 1, which is that one. Okay, look, there is no other this is the bond. There's no hydrogen here. There's no hydrogen there. So there is no neighbor for this hydrogen. These 3 together, they are all equivalent, chemical equivalent. They are, imagine they are 3 boys. They are the same. Or 3 girls. They're the same. Okay, there is no, if they are 3 boys, there is no girls next to them. Why? Because if there was Coupling happens between girls and boys. Just think like that, okay? Just think like that. They're different, okay? But uh, because they are three boys, they don't couple with each other, and therefore they don't split each other at all, right? So this one is number one. We get one signal, and that signal represents three hydrogen, no coupling. Why? Because they are all equivalent. So now we're counted for 1 and 13. What about the rest of them? Let's have a look at 6. So hydrogen number 6, okay, 7, 8, Y9 is here, okay. So if this is the enlargement of that one, the focus on that one, this is 9, the rest of them. Why is 9 a little bit de-shielded than 6 and 7 and 8? Because look, 6, 7, 8, they are not close to any electronegative atom, right? They are not close to any electronegative atom. They are close to the benzene ring. They are all they are all close to the benzene ring. Let me do that again. Get an eraser. I want to erase this. Good. And then I'll go back to the pointer. Okay. Let's count. Let's consider ortho, meta, and all those things. Okay. So as simple as this, right? As simple as this, 9 here, 9 is closest to this oxygen and that oxygen as well. So what do we get? We get this one a little bit more de-shielded, so we get it down here. Okay. What about 6 and 7 and 8? They are, okay, 7 and 8, 7 and 8, they are a little bit far away from this oxygen, from that oxygen, from that oxygen. Therefore, we get them here. See, 7 and 8. And 6, a little bit close to this oxygen, and that oxygen maybe, spatially. Therefore, what happens to this hydrogen? It will be a little bit more de-shielded than 6 and than 7 and 8. Together, what we get a complicated overlapped signal. But in fact, this is a doublet. Why is it doublet? Because there's no neighbor here. There's one neighbor here. So that's a doublet. I don't know why it's doing that. So this is a doublet. That one. 6 is a doublet, right? Easy. And 7 is one neighbor, two neighbor. It's a triplet. Right? It's a triplet. And 8 is a doublet as well. Do you see? Do you see? So this is together a doublet and a triplet. What happens to them? You can't separate them really. Maybe that's 8. Maybe that's the doublet for 8. Maybe this is a doublet for 6. And then there's a triplet for 7. But in fact, what happens? They are all overlapped together. 2, 4, 6, 8. 4 looks like a 4 doublet. Basically, we're not trying to find out what it is. What it is, individually, this is a doublet. That is a triplet. That's a doublet. What happens to these three? Because they're very close with each other and their shielding are very close to each other. Their shielding and de-shielding. Therefore, what happens? Their signal are overlapping together and is not easy to see. This is a pure indication of benzene ring as well, and of a complicated overlapped signal. 9, look here, 9. Why do we get? Okay, we go to 9. Okay, so 9 here. Why do we get a doublet for 9? Because 9, there's no neighbor here. There's just one neighbor here, 8. So 8 splits 9 into a doublet. And that's what happens. Simple as that. And that is the proton NMR of spectrum of aspirin. Aspirin is easier to explain. Paracetamol a little bit difficult. So let's pay attention, ladies and gentlemen. This was in final lab exams and people struggle with it. Okay, so that is one. There's one group of hydrogen. There is another hydrogen. Okay, there is another one here. There is another one here. Okay, there is another one here. Pay attention, please. This is another one here. And there is another one here. So how many do we have? 1, 2, 3, 4, 5, 6, 7. This is the 7. This is a 7 hydrogen. Okay, 7 usual hydrogen. 7. But how many NMR hydrogen? What do I mean by NMR hydrogen? Hydrogens, protons that they are non-equivalent. Okay, this is one of them, one environment. We call it proton environment. This is one environment, and definitely this is another environment. Why? Because this is completely different from everyone else. This is another environment. We'll leave it for later. Okay, okay, this is here, this group here. Okay, so next to it is ortho, right? And this one is meta, right? And if we go back that way, this is ortho and this is meta. So these two are equivalent. So that is number 3, right? The equivalent, the number 3. Meta, these two are equivalent as well. So that is number 4. Okay? Don't do that. So number 4, and this hydrogen is actually number 5. So if I ask you, I honestly, one of my questions, 1 mark, I said, tell me how many numbers of NMR hydrogen is in paracetamol. Okay, how many different proton environment. Okay, we call it proton environment, hydrogen environment, number of hydrogen, NMR hydrogen, whatever you want to call it. My purpose is, what I'm saying is how many hydrogen there are in paracetamol that they can create individual signal, NMR signals. So I say 5. Some people say 7, some said 8, some said 9. Why? Is even if you make a mistake, it should be 7, but they're not 7 because these two are same environment. These two are same environment. So this is 1, 2, 3, 4, 5. I only wanted the student to write 5, and that's 1 mark. Just that. Number 5. That's all I want. What we get 1 signal, 2 signals, 3 signals, 4 signals, 5 signals. That's all we get. 5 signals, right? 5 different environments. Now, how many? What about splitting? Okay, so basically this is a little far away, but this is close to a carbonyl. It's gonna be difficult to pinpoint these, right? When we do NMR spectrum, proton NMR spectrum for paracetamol, we get this. Okay? We call this one A. We call this one A. Right? We call this B. Why is he doing that? We call this B, and we call these two C. We call these 3 D, and we call this one E. That's how we do it. Okay, simple as that. Simple as that. These 3 hydrogens, they are 1 signal. And there is no neighbor to them. You might be saying, what about hydrogen B? Hydrogen B is 1, 2, 3, 4 bonds away from A, right? And you say, what about the effect of this oxygen? Well, 1, 2, 3 bonds away. This is hardly any effect, okay? So we get 1 signal here around 1, 1.5, okay? for 3 hydrogens. That's what we get. Okay, good. What about hydrogen B? Hydrogen B is directly linked or attached to nitrogen, and it's really close to this oxygen. Okay, therefore, and it's close to this double bond, therefore this is fully de-shielded. By de-shielded, it means we will see great effect of the external magnetic fields on this one. Therefore, it's downfielded to here. What do we get? We get one singlet. Why do we get one singlet? Because there is no neighbor, no hydrogen neighbor next to it. So there's no coupling. We get a singlet here. Good. What about C and D? Okay, C, they're both equal. Okay, so we get a signal here. For D, we get a signal here. Why D is more de-shielded, more downfield than C? Interesting, yes. Right. C is more de-shielded. Can you see? This is C. It's more de-shielded than the orange, yellow. Is it? Yes. D. So this is D, and this is C. Why? Well, by looking at it, this group here is attached to benzene ring. So this hydrogen compared to this group is ortho, right? And this hydrogen is ortho. If we go back to here, you see that's ortho. Remember, to this group is ortho. These two hydrogens are meta to this group. Okay. Therefore, the effect of this group on these hydrogen is higher than hydrogens. Therefore, these two hydrogens are more de-shielded, the green ones. Therefore, they are more downfield. But the yellow ones, they are meta to this group. Okay, this group here. Therefore, this group's effect on these yellow or D hydrogens is less than the green ones. Therefore, it is less de-shielded, and we get it in here. Now, you might be saying, what about this OH? It's a good question. Go back here. What is this OH doing in terms of these hydrogens? Now, remember, we said these hydrogens, right? This OH is electron giving, not electron withdrawing. Electron giving. So this OH will give electrons to the benzene ring, maybe not equally to all these hydrogens, but nevertheless, it doesn't take any electrons away from the hydrogen. So we ignore the effect of this OH. We just counter the effect of this group. Okay, and this group is electron withdrawing, taking electron away from these hydrogens. Obviously, it will take electrons away more from the ortho, less from the meta. Therefore, the orthos are more downfield than the meta. There you go. We have more downfield than the meta. Okay. Let me get. Okay. Right. I'll go back to the pen. Now this what we get. We get a signal here for the yellow ones and a signal here for the green one. And we know why the green is more downfield, more de-shielded. Now, by looking at it, okay, I'm removing this, moving all that so we can have a better chance to see. Okay, by looking at it, let's have a look at the D ones. D ones are together one hydrogen. They're two hydrogen, but they're equivalent. Okay, and they are okay next to this one is next to that hydrogen, and this one is next to that hydrogen. So basically, what we get this is one hydrogen. So what we get a doublet. a doublet for that one. And by looking at this one, this is one hydrogen, one environment, and they are neighbors to this hydrogen and that hydrogen. Okay, so what we get, this will split that into a doublet, this will split that to a doublet. But which doublet? The doublet exactly same location, so we only get one doublet, not two doublet. So we get a doublet and doublet, right? So we have a singlet. Okay, so we have a singlet for these three, and we have a singlet for that. Okay, we have a singlet for that one, and we have a doublet, two doublet, one doublet for this one, and one doublet for the green ones. So what do we have? We have a singlet, two doublet, and a singlet. What about this one? Let me clean this up. What about, we don't have, what about E? Right, E is nowhere to be seen. Why? Because we just didn't put it there. But let me draw it. So E, this is a hydrogen, right? And this hydrogen is next to oxygen. Yes, it's far away from the benzene ring. So it might be somewhere here or somewhere there. I think because it's close to the benzene ring and is directly linked to the oxygen, we might get it somewhere here. Okay, we might get it somewhere here. Not sure. But how many neighbors there? No neighbor, so we just get one singlet for E. Okay, so that is what we get. For paracetamol, we get 5 signals. 1 signal, 2 signal, 3 signal, 4 signal, 5 signals. Okay, then the next question I asked, I said, how many signal we get? 5. And the next question was for 1 mark. What is the splitting patterns? All you have to say, 1, 2, 3, 3 singlet, 1 and 2, 2 doublet. That's all you have to say, and you get your marks. So that was 2 marks in the final exam. And a lot of people got it wrong, and I don't know why. So by looking at it, this is the actual NMR, proton NMR spectrum of paracetamol. This is 1, 2, 3, 4, 5. In fact, this is the 4. You see, that is the OH. And actually, it's closer to NH rather than close to the benzene ring. So the benzene rings here, this is 3, okay, and this is 2, okay, and this is 5, and obviously this is 1, right? So which one is more deshielded? Obviously this one is more deshielded because it's directly linked to nitrogen and close to this oxygen and benzene ring, so it's more deshielded. This one here, directly connected to oxygen, so close to the benzene ring, is deshielded but not as much as the NH. Okay, so down here, this is the OH. And we know that one, we don't talk about the first one. Second and third, okay, we talked about ortho, which is more deshielded because they are ortho to this group. And the OH group is electron giving, therefore we ignore it. Second one is meta to this group, therefore has least effect on it, so is less deshielded. Where is the doublet? Because the magnetic field for this spectrometer, NMR spectrometer, was not very strong. It didn't separate the signal. So, but in fact, this is a doublet, and that's a doublet as well. Why is that? Because this split that to doublet, and this will split that to a doublet. That's what we get. Let's have a look. This is what we get. We get CH3. Okay, you go back, and this one, okay, now look at this here. Interesting. The OH is now gone into here. is less deshielded than the 2-benzene ring. Now, the effect of this because of the magnetic field. It's very important. Now, some people go to Farouk Hospital. When you do MRI, they charge 500,000 dinar. You go to Bakshin, they charge 130,000 dinar. You go somewhere else, they charge 80,000 dinar. Somewhere else, 250,000. Why? Because of this. Because when they charge 500,000 dinar, because their instrument, the MRI instrument, is newer, more sophisticated, larger. Larger what? Larger magnetic field. And if they have larger magnetic field, the picture is going to be more clear. Okay? Because because they start aligning the protons better and they give a better resolution pictures. Now this instrument that they did NMR for paracetamol with proton NMR was a strong one. Now it gives you OH here rather than here. This is the NH, and that looks like some impurity. This is the doublet, okay? The doublet for this one for the meta, this one for the ortho, and that's for the CH3. Did you see? That is the proton NMR spectrum of paracetamol. That's how we know this is paracetamol. When you get a sample from the border, anywhere from another country, and they ask you, you work in a quality control, they ask you to find out if this is actually a paracetamol or not. If you get this proton NMR spectrum, then yes, that is paracetamol. Okay, but you might have to think about this a little bit. There's some impurity there, maybe some here as well, but that's not a huge thing. Okay, you can use other techniques to find out if they are actually impurities or just noise. Okay, good. And that is the end of it. Please write your lab report explaining all these in your lab report, drawing all the pictures, drawing all the structures, drawing all the boxes, numbers, and everything. So sit down and rewrite everything in your understanding, not copying it from here, so you know how to answer questions when you get in the final lab exam. Okay? And please talk about these as well, TMS and the solvent, and talk about these 4 important points as well. Now you'll be able to answer this question as well. Now you know the structure of aspirin, you know the structure of paracetamol. We've seen these structures so many times, and now you can answer this question as well. Yes, NMR can help us determine the structure by this and this and that. Okay, so we're going to leave this here, and that's the end of it. Please do your lab reports. Please attend tomorrow's session as well. We're taking attendance, and next week hopefully we go back to labs, but if not, we will have another lab session recorded. Thank you, and have a good evening.